ARM processors. So this is a PDF on ARM architecture reference manual. So this is published by ARM itself. So we'll see the portions on ARM architecture. So what is actually ARM? ARM is a reduced instruction set computer or a RISC processor. We know what RISC is. So ARM is an example of a RISC processor, and it has some features. That is, it has a uniform register file, a load store architecture. It has simple, because it's a RISC type of architecture. It has simple addressing modes, uniform and fixed length instruction fields. So it has control over both ALU and the shifter in every data processing instruction. So your first portion is actually about ARM register architecture. So just to give an introduction of what ARM is, I'm talking about these things. So these are some of the features of ARM. It has an auto increment and auto decrement addressing modes. You don't have addressing modes in your syllabus. So just to know some of the features, load and store multiple instructions to maximize the data throughput, and it has conditional execution of all instructions to maximize the execution throughput. So it's basically a RISC architecture, and so it has a good balance of high performance, low code size. Because of the RISC architecture, it has high performance, low code size, low power consumption, and low silicon area. Next, we'll come to the ARM registers. So it has 31 general purpose registers, and each of the general purpose registers are 32-bit long. And at a time, only 16 registers are available. So you have 31 general purpose registers, 32-bit long, and you have only 16 of them available or visible at a particular time. And the other registers are used to speed up the exception processing. So all the register specifiers in ARM instructions can address any of these visible registers. And the main bank of 16 registers, that is the visible registers, is used by all unprivileged code. So you have unprivileged and privileged code, and these are used by the unprivileged code, and these are called the user mode registers. So the user mode means it is the only mode which cannot switch to another processor mode without generating an exception. So it's all in the unprivileged mode, and it cannot switch to it cannot switch to another processor mode without generating an exception. Memory systems and co-processors might allow user mode less access to memory and co-processor functionality than a privileged mode. So more than the privileged mode, the unprivileged mode has less access to the memory and co-processor functionality. You have the link register, which is one of the 16 visible registers. So link register is the register 14. So you have 16 visible registers, and the register 14 is the link register or the LR. This register holds the address of the next instruction after the branch and link instruction. So that's a instruction. Branch and link is an instruction supported by the instruction set of ARM processor. So when such a instruction is executed, the next instruction that should be executed, that address will be kept in the link register. Something similar to program counter, but then program counter will always contain the next instruction and not necessarily in the case of a branch instruction. But link register is only for the branch and link instruction. The next instruction address will be stored in the linked register. So that is when you make a subroutine call, branch to a subroutine. So in that particular case, the next instruction where you return to, that will be placed in the link register. So it can also be used as a general purpose register when you don't have a branch and link instruction. In other cases, you can use this particular register as a general purpose register for other uses also. Then you have the program counter. You know what the program counter is. So register 15 is the program counter. It can be used in most instruction as the pointer to the instruction, which is to instruction after the instruction being executed. So the address being incremented is like that. So it points to the instruction, which is two instructions after the instruction being executed, and all ARM instructions are 4 bytes long. It is 32-bit word. So and are always aligned on a word boundary. This means that the bottom 2 bits of the PC are always 0, and therefore PC contains only 30 non-constant bits. So the ARM instructions are 4 bytes long or 32 bits. The bottom 2 bits of the PC, that is the lower order 2 bits of the PC, is always 0. So PC actually contains only 30 bits. The last 2 bits are zeros. So these are the 2 registers of the 16 visible registers. There are actually 31 registers. Of that, 16 registers are visible. One is the linked register which will point to the next instruction to be executed in the case of a branch and link instruction, and program counter which will point to the instruction 2 instructions away, and the PC, the last 2 bits of PC will always be 0, so you have only 30 bits. The remaining 14 registers have no special hardware purpose, so it is just used as a general purpose register, the other 14 registers, so they don't have a particular use. They use defined purely by the software. So whatever instruction you write, depending on the instruction, each of these registers will have a particular role. Otherwise, they don't have any allocated role as such. And the stack pointer is normally R13, or register 13 is normally the stack pointer. So going into a little more detail about the registers. The ARM processor has 37 registers. So just before we talked about 31 general purpose registers. So you have 31 general purpose registers, including the linked register and the um, program counter, and R13 is the stack pointer normally, and another 6 registers, those are the status registers. So all these registers, these 31 general purpose registers as well as 6 status registers, all are 32 bits wide, but only 12 of the 32 bits are allocated or need to be implemented. So all the 32 bits are not used, only 12 bits are allocated. So these registers are arranged in partially overlapping banks with a different register bank for each processor mode. So you have different modes of operation. We talked about it, we mentioned it, privileged and unprivileged modes. So depending on the mode, the register banks are overlapping. So 15 general purpose registers R0 to R14, you have that at any point in time. 102 status registers and program counter. So these are the registers which are mostly visible. So this is the register banks, and these are the different modes of operation. You have the system mode, supervisor, abort, undefined, interrupt, fast interrupt modes, of which the supervisor, abort, undefined, interrupt and fast interrupt are called exception modes, and all these are called as the privileged modes. So the general purpose registers, the 31 general purpose registers R0 to R15 will be visible. So that is the 16 visible registers. So in that, R0 to R7 is unbanked register, and you have banked registers R8 to R14. R0 to R7 is unbanked, R0 to R7 is unbanked, and R8 to R14 is banked. R15 is the PC, as we already told. So what is this unbanked register? R0 to R7. So they are called as the unbanked registers. This means that each of them refers to the same 32-bit physical register in all processor modes. So we told that there are different processor modes. So in all these processor modes, R0 to R7 will have the same role. They all refer to the same 32-bit physical register. Okay, that won't change in any of the mode of operation. So they are completely general purpose registers with no special uses, uh, and can be used whenever an instruction allows a general purpose register to be specified. So R0 to R7 is purely general purpose. You can use it in any mode, anywhere, as you specify in the instruction. Now, what is the difference between banked and unbanked? So R0 to R7 is just the general purpose register like we normally use. Banked registers R8 to R14. Okay. R15 is program counter. So R0 to R7 is banked, sorry, unbanked, and R8 to R14 is banked. So what is it? The physical register referred to by each of them depends on the current processor mode. So what is the current processor mode? That will decide the physical register referred to by each of them. Where a particular physical register is intended without depending on the current processor mode, a more specific name is used. This name will come later on. Almost all instructions allow the bank registers to be used wherever a general purpose register is used. So if there is a restriction on the use of bank register, that will happen on R8 to R14, those registers. So if there is a restriction on the use of bank registers, then R8 to R14 cannot be used. For example, R8 to R12 are subject to such restrictions even in systems in which some mode is never used, and so only one physical version of the register is ever in use. So if there is a restriction on the use of banked registers, then that will apply to R8 to R14, that range of registers. And R8 to R12 have two banked physical registers each. One is used in all processor modes and other than the FIQ mode, and the other is used in the FIQ mode. Okay, so it has two, R8 to R12 has two physical registers each. So each of the registers from R8 to R12, each of them have two banked physical registers. And one of these two is used in all processor modes other than the FIQ mode, and the other one is used only in FIQ mode. So you have a register from R8 to R12. Each of them has a register which can be used only in FIQ mode, and the other register can be used in all other modes. So if you have to be specific about the version, uh, about the which version it is being referred to, the first group of physical registers which is used for all the modes, that is referred to as R8 underscore user to R12 underscore user, and the second type which is used only for FIQ mode, that is referred to as R8 underscore FIQ to R12 underscore FIQ. So what we mean is, see, if you have R8, R8 is not a single register, it has two physical registers. One is what? One is called R8 underscore user, which is used for all the modes except the FIQ mode, and R8 underscore FIQ is used only in the FIQ mode. So similarly, for all the registers from R8 to R12, all of them have two physical registers. So R8, when you say R8, there are two types. R9, you have two types. Likewise, till R12, you have two registers. Depending on the mode of operation, you will be using one of them. So these registers R8 to R12, they don't have any special purpose, like in the case of program counter or link register or any of these. They don't have any dedicated special purpose, but for interrupts that are enough simple to be processed using R8 to R14, The existence of separate FIQ mode of these registers allows very fast interrupt processing. So if you want to process an interrupt which using R8 to R14 those registers, then you will make use of these registers to process those interrupts. So these are two examples. I'm not going into details. DMA transfers, a direct memory access transfer. So uh, direct memory access is requesting for the buses by an external uh, entity. So when you have any such request that will be taken as an interrupt, then you can make use of these registers. And registers R13 and R14, because we talked about only R8 to R12. You have R13 and R14 also in the set of banked registers. So these two have 6 banked physical registers each. So R8 to R12 have two physical registers each, and R13 and R14 have 6 each. One is used in the user and system modes, while each of the remaining is used in one of the 5 exception modes. So user and system modes you have one, rest 5 is used in one of the 5 exception modes. So you have 5 exception modes, and each one is used in each of these exception modes. So they are represented like this: R13 underscore, and which is the mode, R14 underscore mode. Mode is the like user or SVC, supervisor mode, ABT, UND, like that. So that will define which is the uh, which mode that particular register refers to. So we already said that R13 is used as the stack pointer normally, and it's called as SP. So we normally use R13 as the stack pointer. R14 is also known as the link register, and we told what link register is in branch and link instruction. The next instruction address will be stored in the link register, which is the R14. R15 is the program counter, and R13 is the stack pointer. So R15 is the program counter. So what is the use of program counter? Reading the program counter. When an instruction reads R15 without breaking any of the restrictions on its use, the value read is the address of the instruction plus 8 bytes, because each instruction is 32 bits long. The current instruction plus 8 bytes will be the address of the next instruction. So this is one of the examples. Subtract R1 comma PC hash 4. So R1 is the address of the following instruction, which is str, this instruction. Next is the program status register. So we said that you have status registers also. So this is the program status register. So the current program status register or CPSR is accessible in all processor modes. Contains the condition code flags, interrupt disable bits, the current processor mode and the other status and control information. So we have talked about program status registers before, which will contain condition codes or flags, which will determine the, like, after the execution of a particular instruction, the carry is set, overflow is set, zero is set. So that will be recorded inside the program status register. So in ARM processor, you have a program status register which is called the current program status register, and that is accessible in whatever mode the processor is in right now, and it contains the flags just like we have already discussed. So all the status and control information will be recorded inside that particular register. So the CPSR, this is the format of the CPSR. So N is negative, Z is 0, C is carry, V is overflow, and those are called the flags or the condition codes. Now you have another flag called the Q flag. So that is for ARM 5. So we need to know about that. So you have some interrupt disable bits in the program status register. So that is the I bit, F bit, I bit, F bit, T bit, these. So these are bits which will disable the interrupts which is coming in. So if you want to disable the interrupts, just set these to 1. So I bit will disable the request or the interrupt which is called IRQ, interrupt request. F bit will disable the FIQ interrupts. These are some interrupts you need to know about it right now. The T bit should be 0 on ARM 3 and below. So if it is 4 and above, we are talking about ARM 7. So 4 and above, T is equal to 0 means it indicates ARM execution, and T equal to 1 means it indicates thumb execution. Then you have the mode bits. These are the mode bits 43210. So that will decide on which is the mode of operation of the processor. So 43210, that is specified like this. M4 is to 0 means that is 43210. So if the values is like this, then it is in the user mode. This is the FIQ mode, IRQ mode, supervisor mode, abort mode, undefined mode, and system mode. So you can see the values and the modes. So the mode will be specified by setting or resetting the bits in the PSR M420. So there are some bits which are not shown. So those are not used right now. If you want to expand this particular ARM processor in the future, then that will be used. So right now only these many bits are used in the program status register. So 31 to 31, 30, 29, 28, 27 and 720. Only these are used. These are not used. So this is negative, 0, carry, overflow, Q we don't want. These are not used. Then I bit is for the interrupt. F and I, F and T. I and F is for interrupt. T is for arm or thumb execution. And mode bits are for the different modes of operation. So this is what is the register architecture of ARM processor.